All right, let's jump right into it. Welcome to this explainer. I am absolutely thrilled you're joining us today because we are taking on a massive, honestly super exciting goal. We are going to demystify deep learning and TensorFlow. If you've ever looked at machine learning and felt totally overwhelmed by the jargon, stuff like neural networks, tensors, hidden layers, backpropagation, don't worry, you are in exactly the right place. We're going to break all of that down into clear, actionable knowledge. Trust me, by the time we wrap up, you're going to look at the world through a completely different lens.
To kick things off, I want you to think about driving a car. Like, really think about it. If I asked you to sit down right now and manually write out every single rule for driving, could you actually do it? I mean, you'd probably start easy, right? Stop at a red light, steer left, go left. But what about interpreting a pedestrian's body language on a busy corner, or instantly adjusting to a sudden patch of black ice? You quickly realize the rules are practically infinite. And this brilliantly highlights the limitations of traditional programming. For complex, real-world problems, we literally can't code all the rules by hand. We absolutely need a new approach.
So here's our roadmap for today's explainer. 1. What is deep learning? 2. Inside a neural network. 3. What exactly are tensors? 4. Enter TensorFlow. And finally, 5. Building your first model.
Okay, Section 1, what is deep learning? Get ready, because we are about to fundamentally change how you view computer programming.
Traditional programming, right? You start with inputs, you write the rules, and you get an output. It's kind of like your Sicilian grandmother's famous chicken recipe. You take the inputs, the raw chicken, the veggies, and you follow her strict coded rules. Cut this, preheat that, cook for exactly 30 minutes to get the beautiful output of a roasted dinner. But machine learning? It completely flips the script. In machine learning, you provide the inputs, the raw ingredients, and the ideal outputs, like photos of perfectly cooked chicken. The algorithm's job is to figure out the rules to get from A to B. We just showed examples, and it basically learns the recipe itself.
Look, if you search online for a definition of deep learning, you're going to get hit with a massive wall of academic jargon about extracting progressively higher-level features and so on. Let's just strip all that away right now. I want you to focus on this one simple, empowering definition that's going to act as our guiding star for this entire explainer. Machine learning is simply turning data into numbers and finding patterns in those numbers. That is it. Whether you're predicting housing prices or solving some 50-year-old protein folding challenge, this is the core mechanism.
So you might be wondering, where does deep learning specifically shine compared to older, traditional machine learning? Well, traditional algorithms like random forests, they're fantastic for structured data. Think of neat little Excel spreadsheets with rows and columns for car sales. But let's be real, the world is messy. Deep learning and neural networks specifically absolutely dominate when handling messy, unstructured data. We're talking about millions of pixels and images, complex natural language and emails, or raw, chaotic sound waves.
Moving right along to Section 2, inside a neural network. Now that we know what deep learning is, let's pry open the black box and see how it actually works.
Let's track exactly how a network transforms raw information. First, we take our unstructured data, say an image of a bowl of ramen, and numerically encode it. We turn it into numbers. Second, we pass those numbers straight to the network's input layer. Third, the data flows through the hidden layers, which do the heavy lifting of finding the hidden patterns within those numbers. And finally, the output layer generates a prediction, giving us back human understandable information, like slapping a ramen label on the image.
So the absolutely crucial point here is that those hidden layers are where the magic happens. You could have one hidden layer, or you could have 150. When a neural network first wakes up, it initializes these layers with completely random starting weights. But as we feed it more and more data, it constantly adjusts those random patterns to better match the ideal outputs. Actually, think of it like a massive trial and error machine that just relentlessly self-corrects until its internal math maps perfectly to the right answer.
All right, Section 3. What exactly are tensors? We really can't talk about TensorFlow without unpacking the tensor part of the name, right? So let's get into it. Remember our guiding star definition, turning data into numbers? Well, a tensor is quite simply the container for those numbers. It's the standard numerical way we represent information so that our machine learning algorithms can actually process it. If you're feeding data into a neural network, it's going in as a tensor.
A tensor is just an n-dimensional array of numbers that can scale up infinitely. A rank 0 tensor is just a scalar, a single number, like the number 7. A rank 1 tensor is a vector, which is just a list of numbers. Step it up to rank 2, and you've got a matrix, kind of like a 2D Excel sheet. But we don't stop there. A rank n tensor is an n-dimensional array. Whether it has 0 dimensions or 1,000 dimensions, in the deep learning world, we just consistently refer to the whole shebang as tensors.
I'm bringing this quote up again because you really need to drill this mantra into your head. It represents the absolute bedrock of everything we're building. Data to numbers, numbers to patterns. We take images, turn them into tensors, which again are just arrays of numbers, pass them through the hidden layers of a neural network to find patterns, and spit out a new tensor that gives us our prediction.
Section 4, Enter TensorFlow. We've got the theory and we've got the data structures. Now, let's introduce the engine that actually makes all this numerical crunching possible.
So TensorFlow is this incredible end-to-end open-source machine learning platform originally built by Google. It lets you write super fast deep learning code, usually in Python. And this is the game changer. Run that code on high-speed hardware. Because searching for patterns in millions of numbers takes serious juice. TensorFlow seamlessly distributes your math across graphics processing units, or GPUs, and tensor processing units, TPUs, which are custom chips literally designed just to crunch tensor math at lightning speed. It handles the whole pipeline, from pre-processing data to deploying your model into a live app.
Now, right before we transition to actually writing some code, I want to remind you of something super important. Building models isn't about being this rigid chemist where everything is measured out to the perfect millimeter. It's way more like being an experimental cook. Your grandmother tweaks her recipes, throwing in a little seasoning here, a little there. That is exactly how you should approach TensorFlow. If in doubt, just run the code. Try adding a new layer. Tweak the data. Experiment, experiment, experiment. Which brings us to Section 5, Building Your First Model. Let's see how all these concepts translate into practical code by throwing together a beginner-friendly image classification model.
This exact sequence is pulled straight from the TensorFlow Quick Start Guide, and it cleanly lays out the pipeline for building your very first classifier using Keras, which is TensorFlow's high-level API. It's just 4 steps. Load our image data, stack our neural network layers, compile the rules for how it learns, and train it to find those patterns.
The crazy thing here is how simple stacking these layers becomes when you use this sequential function. First, we load our image pixels, which normally range from 0 to 255, and we just scale them down to a 0 to 1 range to make the math easier for the network. Then, using tf.keras.sequential, we literally just stack our layers like Lego bricks. We drop in a flattened layer to line up the image pixels, dense layers to act as our hidden pattern finders, and a dropout layer to randomly turn off some neurons, which is a neat trick to prevent the model from just stubbornly memorizing the data.
Okay, so your layers are stacked. Now you have to compile the model. Compiling is basically just telling your model, hey, here is exactly how you measure your own mistakes, and here's how you fix them. We define a loss function like sparse categorical cross-entropy, which just scores how wrong the predictions are. Then, we set an optimizer, like Atom. The optimizer is the navigator. It actively tweaks those random starting weights in the hidden layers, trying to push that error score down as close to absolute 0 as possible.
And here is the incredibly satisfying payoff. By simply fitting this model to our data, we teach it to recognize the patterns in our images. If you follow these basic steps on the standard MNEST dataset, you get a model that is roughly 98% accurate at classifying images it has literally never seen before. 98%. And the wild part is, you've built it using the exact same underlying architecture that powers cutting-edge self-driving cars and voice assistants.
We've covered a ton of ground in this explainer today, from the core theory of deep learning to tensors and the raw power of TensorFlow. But I want to leave you with this final provocative thought. You can use machine learning for literally anything in the universe, just as long as you can convert it into numbers and unleash an algorithm to find patterns in them. The potential here is absolutely limitless. So, armed with this new understanding, what are you going to turn into numbers next? Thanks so much for joining me. Keep experimenting, and I'll catch you next time.